Okay, so this is Overengineering Max. It's a really fun talk. I had a lot of fun preparing it and actually implementing all the stuff I'm talking about. Hope you do too. So in this talk, we're going to implement max AB. We're also going to talk about accidental and essential complexity. And we're going to look at the worst feature C++ has ever added. I think this feature has caused like so many problems in C++ evolution. It really should have never been added. And it's not one you expect. So this is what we're going to do. We're going to implement the maximum function maxAB, which returns the greater of the two arguments. Right? How hard can that be? I mean, this is it, right? Max int AB. If A is less than B, then we return B. Otherwise, we return A. People usually use the ternary operator for that, just like one return statement and then one expression, very concise. Of course, we're not quite done. We need to do all these fancy annotations. It's no discard, it's const but it's no except. But let's ignore those, otherwise the code wouldn't fit on the side. So of course, this is a talk about C++, so this isn't good enough. Let's make it generic. It's very easy. Just write a template type name T, replace all the ints with T's, and do the implementation. Are we done? Is this a generic version of max? And the answer is no, because every time you write a generic function, you need to think yourself, what are the type requirements? We cannot just pass any type to max. It has to fulfill certain requirements. For example, we've got syntactic requirements. The type T must provide an operator less than that returns something contextually convertible to bool. Otherwise, we can't do comparisons. More important are the semantic requirements. This operator less than must do comparison. And to be precise, it must implement a strict total order. So let's talk about order theory for a bit. So a strict total order of a set S is a binary relation less than that has three properties. So a binary relation is just something that relates to elements. Formally, like it's a subset of S cross S, but it's just a pair of elements. We can implement it in C++ as a function that returns true if two elements are in a relation. And it can't just be any relation, it needs three properties. The first is irreflexibility. It's a strict order, so A is not less than A for all elements, right? It's less than, not less than or equal. The second is transitivity. If A is less than B and B is less than C, then A must also be less than C for all possible triples A, B, and C. And because it's a total order, we have the law of trichoton, whatever. For all A and B in S, either A is less than B, A is equal to B, or B is less than A. All elements need to be like in one of those three states, because otherwise like it has to be like it's a comparison. And so let's annotate those requirements. We have generic functions, and T has an operator less than that implements a strict total order. I could also use concepts or requires clauses, but like we can't really express semantic requirements in concepts anyway, so let's just write in the comment to state the requirements. Are we done now? Well, we've got a generic function. It works. We have the correct requirements, but the requirements are maybe a bit too strict. So for example, let's say we have a person. A person has an ID and a person has a name. And now we want to compute the maximum of two people by name. And since our max function doesn't take like a comparison function, we sort of create this wrapper type who does the correct comparison semantics. So it just has a pointer to the person and compares them by name. And now we can compute the maximum of people by comparing them by name. The problem with that is if we consider a call like this. So P1 is a person with one ID called Jonathan, and P2 is also a person with an ID also called Jonathan. And this call violates our semantic requirements. Because according to our comparison, P1 and P2, P1 is neither less than P2, and P2 is neither less than P1, but they're not equal, right? They're two different people, they have different IDs. So we violate the law of trichotonomy. Just because two people have the same name doesn't mean they're equal. Like there are three people that are called Jonathan that are giving a talk today, and we're all different people. So we don't have a strict total order. But max still works. This indicates that our requirement is maybe too strict. And what we actually want here is a strict weak order. So a strict weak order is also a binary relation, but it's a weaker form of a total order. So we still have irreflexibility. It's still strict, so A is not less than A for all elements in our set. It's still transitive, so if A is less than B and B is less than C, then A must be less than C for all triples in our set. But we have only two weaker properties instead of trichotonomy. So asymmetry means that if A is less than B, then B must not be less than A. Right? An element can both be less than in both directions. This wouldn't make any sense. And now every less than also defines an equivalence. So let's say A and B are equivalent if neither A is less than B nor B is less than A. And we want this equivalence, which is like a weaker form of equal, they are equal according to this less than relation, to be transitive. So if A is equivalent to B, which means neither A is less than B nor B is less than A, and B is equivalent to C, then A must also be equivalent to C. Now what this means mathematically is that we have a strict weak order implements a strict total order on the equivalence classes according to tilde. But what this just means that if we take our set and we group all elements together that are equivalent according to our strict weak order, then we've got a strict total order. In the case of people, if we group all people with the same name together and consider them equivalent, then we've got a total order of the resulting thing after the grouping. So it's just a total order, but like we relax the requirements of equal. Right? They don't need to be equal, they merely need to be equivalent. And so if we say that this is our requirement, T needs to implement a strict weak order, then this code works. We don't violate the semantic requirements. I mean, it worked before, but now we also don't violate the requirements. But it has an interesting question. What should the result be, right? According to the strict weak order, they're equivalent. So max cannot distinguish between them because they both have the same name. But if we look at the result, we can distinguish, we know which one max picked because we can look at the AD and the AD difference. So it makes a difference whether max returns P1 or P2. And which one should it be? So this is the implementation we have right now. We say if A is less than B, then return B. So in this case, A and B are equivalent. So A is not less than B, so we return A. So with this implementation, we would return A. So P1 is being returned if they're equivalent. If they're equivalent, we return the first argument. There's an argument to be made that this implementation is more correct. Here we flipped it around. We asked whether B is less than A, and only then do we return A, otherwise we return B. And so here, for equivalent elements, we return the second one. And since we return a maximum, in some sense, it makes more sense to return the second one because it's like further in the list, so it's like automatically bigger than the first one, in some sense. It's a nice symmetry there. But stdmax goes with the first version, so when equivalent, they return the first element. So let's just stick with that for now. And so now we've essentially implemented stdmax. The first version is exactly what stdmax does, but I'm 7 minutes into this talk, so we are far from done. Because our function takes a single template argument t, which means code like this doesn't compile. We've got a string, and we've got a string view. We want to find the maximum. This is an error. Because there is no single type t that works. We pass in 2 different types. It's easy to fix though. Just add in a second template parameter. Now we take t and u. The requirement is that together they have a common operator less than that works. And the implementation is unchanged. Interesting question now is what is the return type? Right, we just use auto and have the compiler figure it out. But there's actually like, how can we spell that type if we don't want to use auto? Well, for that we can use std_comment type. So std_comment type is typedef and essentially returns whatever the ternary operator does. It also has the nice benefit that if there is no comment type, so if we pass, let's say, an int and a string, then our call to max will not compile because it just is out because we don't have a comment type. And comment type is a pretty weird type trait. So it's essentially that. The comment type of t and u is the decal type of the ternary operator after decaying both arguments, and then we decay the result. So this means that the result of comment type, it's never const qualified, it's never a reference, it's always a decayed type. Then there are a bunch of weird exceptions added in C++20. So because for some reason, sometimes this type doesn't exist, but if you do the decal type of the type where we pass like const lvalue references instead of decay of t and u, then it works. And I don't know why this exception is added. I asked some people around on the committee last week. They also don't know what this exception does. It was just something necessary for ranges or whatever. So it's a bit more complicated than that. But like in a nutshell, it's essentially that. The weirdness doesn't stop there. Comment type is also user customizable. It's one of the only type traits. It's the only type traits in type traits that you can specialize for your own types. So you can specialize, say, this is my type A, this is my type B, this is their comment type. And so you could say, like the standard library could say something like, the comment type of T and std null opt is optional T. This seems useful until you try it out and learn that this does not affect the ternary operator. So even if you add a specialization for like T and null opt to result in optional T, you cannot use it in a ternary operator, which kind of defeats the point. So I don't know why we can customize it, but we can. It just doesn't affect the language in any way. But the weirdest thing about this is that common type T is variadic. So we can pass multiple arguments and have the common type of all of them, but it's not associative. This means that we can define 3 types A, B, C, such that the common type of A, B, and C is not the same as the common type of B, C, and A, which is pretty bizarre. And we don't even need to do any customization for that. All we need to do is this class hierarchy. So we've got A, and then 2 classes, B and C, both derived from A. On the left-hand side, the way common type T is implemented, it first checks for the common type between A and B. This is A, because that's a type both are implicitly convertible to. And then we compute the common type of A with C, which is also A. So on the left-hand side, we get A. But on the right-hand side, we want to find the common type of B and C. And even though, in some sense, there is a common type, like both B and C convert to A, this is never considered. So the result of common type is only looks at one of the types in the arguments and never like some arbitrary third type that they both might be convertible to. So the common type of B and C does not exist, which means we immediately have a hard error on the right-hand side. And this is pretty weird behavior. But anyways, now using common type and the 2 template arguments, this code just works and it prints world. So let's do it with some actual math objects and say we want to find the maximum of int and int -1 and the unsigned int 1. What does this print?
Cited values.
Yes, it prints 4,294,967,295. Because that's obviously, I mean, to be fair, it is bigger than -1 and 1, but it's not quite the maximum we're looking for. And there are actually 2 things that are going wrong here. The first one is the signed-unsigned comparison. So let's say we want to compare an int and an unsigned. Now there are 3 potential choices on how this could be implemented. We could compare the mathematical value they represent. So negative values are less than all unsigned values. This would be correct, so it's obviously not what C++ does. We could convert both of them to int and compare to ints. This would be wrong because it would convert big unsigned integers into very small signed integers. But C++ doesn't do it. C++ instead is wrong in the other way. It converts both to unsigned and then converts to unsigned. So negative integers become really big unsigned integers. In C++ defense, in C++ 20, we added std less and some other comparison functions, and they implement the correct thing. So they implement option 1. The functions you can call, you can give it to numbers, and they will accurately report whether one is less than the other by using the appropriate logic. But built-in less than does the wrong thing. But even if less than were to be fixed, we still run into the second problem, which is that the common type of int and unsigned. It can be the correct thing, which would be the next larger signed integer type that can fit both types. So in this case, it's probably long, right? Let's say a long can contain a value of an int and an unsigned and also of an unsigned. So that is the type that both can convert to. So this should be the common type. This would be correct, but C++ doesn't do it. And can't really blame it because like eventually you run out of larger integer types. And it would be weird if it works for int and unsigned, but not long, long and unsigned long, long. So it doesn't do that. We could say it's int. This is the same consequence that like large unsigned integers get small integers. But instead, C++ makes them both unsigned. So the negative integers become very big unsigned numbers. And neither of those options are particularly satisfying. So I think we actually pick the 4th option. We make it invalid. We say that int and unsigned don't really have a common type. Because while there is a type they both implicitly convert to, there is no type they safely implicitly convert to. So we have this concept, safely convertible to. It's essentially std convertible to, but also that conversion needs to be safe. So conversions that aren't safe is, for example, slicing. If you slice a derived class to a base class, that is unsafe because we throw away information. You can convert a derived reference to a base reference, but not like a derived non-reference to a base non-reference. String to string view is implicitly convertible, but that conversion isn't safe because it's potentially dangling. And of course, we do the correct thing for all arithmetic. So like int to unsigned is not a safe implicit conversion. And this is implemented by doing the appropriate logic for the built-in types and then having specializations to opt in to various class types. And then we've got our own version of TC comment type. So TC comment type is std comment type, but we require that it's safely convertible to the comment type. So if it's not safely convertible, then we say the comment type does not exist. So even though int and unsigned have a std comment type, they don't have a TC comment type because they're not safely convertible to that. And so if we use TC comment type as our return type, if it compiles, it's still the same type. But if we actually call it with an int or an unsigned, this will be an error because they're not safely convertible. TC comment type T doesn't exist, and so we don't find an overload. And that way we sort of implemented safe mixed comparisons by simply not allowing them and having you to do some extra work. Any questions at this point? Okay. So let's continue. Let's support perfect forwarding. So this is our implementation right now. And let's say we want to compute the maximum of 2 strings again. This is, we have run into a bit of a, it works, but it's not nice because TC comment type, just like std comment type, is never a reference. So even though we're both passing 2 strings, like we create an unnecessary copy. Like the function returns a prvalue, so we create an unnecessary copy of the string. This particular case is quite easy to fix because we can see, okay, so if T and U are the same type, then we don't need to return the comment type, we can just return a const lvalue reference to that type, right? So something like this. So if they're the same type, just return a reference to that type, otherwise return the comment type. And now when we call it with 2 strings, we will simply get the reference out. That's easy to fix. But let's say we use max like this. So we've got an lvalue string view and an rvalues.string. They are not the same type, right? So a string view and a string aren't the same type. So we don't get the optimization, and instead we return the comment type. The comment type will be a string. So we will copy the rvalue string into the result, even though we could move it. But we lost that information because we pass everything by lvalue reference. So let's actually use forwarding references. So now we use forwarding references to accurately capture the value category of the thing. I'm not quite sure about the return type yet, so let's just use type auto for now and have the compiler figure it out. But I still want the constraint, so I constrain the function to say that the comment type must exist. If the comment type doesn't exist, we don't call the function. But we don't use the comment type as the return type because the comment type would never be a reference, and we want to return a reference. I want to understand what exactly the return type is. In particular, I'm curious about the case, what if we're essentially passing the same type? We're just passing different const and cbref qualifiers of the same type to max. So what's happening here? What does the ternary operator return? And for that, I built the following table. So the ternary operator between the various cbref qualifiers of 2 types. And we have, it's symmetric, which is nice. So it's commutative, which is a good sign. And then there are like 3 sections. So if we have an lvalue reference and another lvalue reference, the result will be an lvalue reference, and it's const as soon as one of them is const. This makes sense. Same thing happens for rvalue references. So it stays an rvalue reference, we just add const as soon as we need to. And then if we mix an lvalue reference and an rvalue reference, we get a prvalue. So the result is a prvalue when mixing an lvalue and an rvalue reference. So when we have our implementation, we know it returns a prvalue when mixing. This means that when we call it with 2 strings, one is an lvalue and one is an rvalue, we will get a prvalue. And again, this leads to an unnecessary copy of A, because we need to copy A into the result, even though there is no need to do it, because both objects live long enough to be printed. Right? The lvalue lives long enough anyway, and then when we pass the rvalue, the prvalue, this will trigger temporary materialization conversion, create a temporary object that will be destroyed at the semicolon. So it would be perfectly fine to return a reference. But the ternary operator doesn't do it and returns a prvalue. So maybe this isn't quite the correct return type. What we actually want is sort of to use a return type that is like comment type, but also is an actual reference. And such a type that exists. It's called std common reference. So std common reference, if we pass it types that are sort of like the same modulo cbref qualifiers, it figures out the correct combination of cbref qualifiers and is that. Otherwise, it falls back to std common type. So the common reference of like a string and a string view is still a std string without any reference qualifiers. But if we pass in like a string lvalue and a string rvalue, it will somehow figure out the correct thing. More precisely, this is the relevant table. It's still symmetric. The top left and the bottom right haven't changed from the ternary operator. But if we mix an lvalue reference and an rvalue reference, we will get a const lvalue reference. So stud common reference is a const lvalue reference when mixing an lvalue and an rvalue reference. And this makes sense because this is the implicit conversion graph for references. So we can always add const. We can turn a tref into a const tref, and we can turn a tref into a const tref. And we also can convert everything to a const tref. So if we use const tref as like the common reference, this is the universal receiver. When you pass a function that wants to accept anything, you take a const tref because it accepts anything. All kinds of references implicitly convert to that. Now, let's think about this choice from a language design standpoint. Is that really the best choice? This is the relevant table. So when we've got an lvalue reference that is not const, it does not bind to temporaries, it does not bind to const. And the only thing that binds to rvalue references are const lvalue references or rvalue references, and you need a const qualifier in order to accept const. And because of this yes, yes column in the const ref case, functions that don't care about lifetime augmentation use that. And there is some, like we've got two yes, yes columns, but we're missing the case of does not bind to temporary, but does binds to const. So there is a bit of a asymmetry there. And it makes sense that it's implemented that way because when we added lvalue references, rvalue references weren't a thing. So we had to make that choice. But like, if we had a time machine, would we still make this choice? And I'd argue we wouldn't. So let's take a time machine, go back, and design this table. So now a const tref does not bind to a temporary. And the universal receiver becomes a const tref. So if you write a function that doesn't care about lifetime augmentation, you use a const tref. And I'd argue this is a better world, because it means that every time you have an lvalue reference, it will never be bound to temporary, and every time you have a const object, it can potentially be bound to const. And so if you don't care about mutation, you use a const references, and if you don't care about lifetime, you use an rvalue reference. But if you use an lvalue reference, you've got some guarantee that the thing is an lvalue, and it's safer to store them somewhere, right? So if you've got a regular function that takes a const ref, you cannot safely take the address, store it somewhere else, because it could be called with a temporary. But under this world, it wouldn't. So we argue that this is actually the better choice. And so just to see the implicit conversion graph in that case, now everything is implicitly convertible to const ref instead of const ref, and so that is the universal receiver. And we like this design so much, we sort of pretend that this is the world we live in. So our common reference, just like we have a common type, first of all, it builds on top of our common type instead of stud common type. And then it says that the common reference of an int ref and an int ref is a constant ref, not a constant ref. Because we argue this is the more correct choice, because we don't lose track about the fact that we have a potentially rvalue reference in there. It has a bunch of really annoying consequences because the language doesn't work that way. For starters, our common reference, the input types aren't implicitly convertible to the common reference, because you cannot implicitly convert an lvalue reference to a const rvalue reference. Even though there's nothing wrong with it, it's just not allowed implicitly. So we have to do a bunch of static casts in weird places. And also our conversion traits, they lie about that and pretend this conversion exists, but it doesn't. It creates some frictions, but overall it solves a lot of problems. My boss gave a talk about it, the rvalue reference lifetime disaster, about like all the ways this sort of behavior fixes a bunch of problems. So to recap, this is the table that we are using, and we changed the top right and the bottom left to use const ref instead of const ref. And so when we use our common reference, we will get, we argue the better semantics, and we still got the safety. So we still prevent this undangerous mixed conversions, but this works. Except, of course, this implementation is broken, because it immediately creates dangling references, because the result of the ternary operator is a PR value. And we say we return a reference. So when we pass in like an int ref and an int ref, and we use the ternary operator, the result will be an int, but our return type is an rvalue reference to an int. So we just return a reference to a dangling temporary. And this isn't necessarily the fault of our TC common reference. The same thing happens with stud common reference. It's just that stud common references and the ternary operator don't agree. The common reference is a reference, the ternary operator is a PR value. So every time you combine them, you immediately have dangling references. This is such a dangerous pitfall, and like no compiler warns about it. It's just only a question of time. So to fix this, to use an if else. You cannot use the ternary operator because the ternary isn't a PR value, whereas here we're keeping the referenceness intact. Of course, in our case, this doesn't actually work because the common reference, like the things aren't necessarily convertible to our common reference. So we might need to use static casts, and then it gets ugly. And when code gets ugly, we fix it using our favorite way to fix it. We have a macro. So we got the macro conditional rvalue as ref, and this is sort of our implementation of the ternary operator. And it's pretty nice. So this is the implementation. We just compute the common reference first and static cast about arguments to it. Now they have the same type. The ternary operator doesn't do any conversion, just keeps it intact. And it also has the side effect that if we specialize common reference, we actually can use the ternary operator. So we have a specialization for null-opt at t that returns an optional t, and we can use that with our macro, which is really convenient. Like we used it in a bunch of places. We also have got some metaprogramming. So we've got a big class hierarchy that uses, like, indicates which base classes are. And when you want to compute like the ternary between like B and D, we do some metaprogramming and common reference to find the lowest common ancestor and just make it work. And likewise, with the plain ternary operator, this wouldn't work. So our macro is better in many ways than the built-in. Any questions at this point? So let's implement clamp. We've already implemented max. It supports mixed comparisons. We do perfect forwarding. We compute the correct common reference. We can also implement min, just switch the thing around. I've omitted the semantic requirements for now. And now we can build clamp. And clamp simply takes the value, the low and the high, and we compute the maximum between the value and the lower bound, and then the minimum of that with the higher bound. And so, for example, we can clamp our string between two strings. And this just works. And in this case, it will return it unchanged, without any unnecessary copies or whatever, it just works. Problem is, if you use one of them as a string view, then this code crashes. Which is a really subtle bug. So let's investigate what's going on here. We're calling clamp with a string rvalue reference, a string view lvalue reference, and a string lvalue reference. The first thing we do is we compute the maximum between v and low. This computes the maximum between a string rvalue reference and a string view lvalue reference. They don't share the same underlying type, so we fall back to common type and return a string PR value. So this is a string PR value, because it's what's necessary. We then compute the minimum between the string PR value and high, which is the string lvalue reference. So this is a string lvalue reference, and the result of a PR value and an L value, in our case, is a const R value reference. But crucially, it's a const R value reference to a PR value created inside the function. We then immediately return it and just return a dangling reference. So this code, when mixing types in this way, just doesn't work. We return a reference nobody is supposed to use. This is interesting, because the question is, like, who's at fault? Like, in isolation, max and min were perfectly fine to do that. Like, they are allowed to return a PR value. And if you call max or min with a PR value, you materialize a temporary object, get an R value reference, and max and min can return it. So, like, in isolation, who's at fault? Let's define some terms. So we say a projection is a function that returns a reference whose lifetime is tied to one of the arguments. Like, max and min are projections. And then a composed projection is a projection that you build by composing multiple projections, like in the case of clamp. And to formalize the problem is, if a projection returns R value reference to PR value arguments, composing them can lead to return dangling reference if the PR value is created inside the composition. Now there is an obvious solution here. That is, a projection never returns an R value reference. Then we can never return an R value reference to a PR value argument, and we completely avoid the problem. So this would mean that, let's say we have a function decay R value, which decays it if it's an R value reference, and then we use that as the return type. So now max will never return an R value reference, it will always return a PR value, so we cannot return a dangling R value reference to a PR value, because we never return an R value reference at all. Very simple, straightforward solution. The problem is it's too aggressive, right? Because it decays it every time, even if it would be perfectly safe. And in the actual code base, we didn't run into this issue with min and max. That would be like acceptable, because how often are you going to compute the maximum of like an array, where like the move is expensive or whatever. But in our case, we actually had the problem with like trim left and trim right, and trim, which was a composition of trim left and trim right. So we want to remove padding, and those functions try to do it in place. And if it's an array, we don't want to copy the array, so we keep the array return as an R-value reference, and then we really don't want to decay. So this solution was just way too aggressive. So let's try a more fine-grained solution. That is, a projection never returns an R-value reference to a p-R-value argument, because that's the problematic case. If you give me an actual R-value reference, fine, but if it's a p-R-value, don't return it. So let's say we have this type trait, decay of p-R-value t, which decays our type t if any of the arguments are p-R-values. So then we use that as the return type. And we say, if the common reference is an R-value reference and t or u are p-R-values, then decay them because it's potentially dangerous. This solution is better. It just has a slight problem. It's not implementable. This is because of the way forwarding references work. So when we have a function that takes a forwarding reference, and a generic function essentially that takes an R-value reference is of course a forwarding reference, so it's not an R-value reference, it can be any of them, and you can call it with an L-value, an X-value, or P-R-value. If you call it with an L-value, T will be deduced to be some L-value reference, and then reference collapsing keeps it an L-value reference. But if you call it with an X-value or P-R-value, T will be just the type without any reference, and then we just add an R-value references. This means that the function cannot distinguish between P-R values and X-value arguments because we just both get the exact same types. And this is really frustrating because it would have been so easy to fix. Right? Just take a time machine and make this the rule. So if we call it with an X-value, T will be deduced to become an R-value reference. And if we call it with a P-R value, T will not be a reference. Then by just looking at T, we can distinguish between L values, X values, and PR values. And by looking at T ref, we still have the same behavior as before. This would be such a simple change that we don't lose anything by doing it, and we just get so much more information in the middle of a function. It would be so nice, but of course it's a breaking change, so we can never do it now. And back in the day, unfortunately, nobody thought of it. This is frustrating. Like, if we had a time machine, this is the first thing I would change. I would go into the committee and say, hey, we should use this rule, then we get more information within our function. And then, because then we could implement the behavior. Like, then we could decay, if we have a PR with the argument, we could decay the resulting reference. But without this change, we can't. It's also, we probably wouldn't actually implement a solution because it's still a bit too aggressive, right? So if we use max like so, and then we return, this is dangling, right? So in this case, we need to decay. But if we just pass it to some other function, which does whatever with it, then it's fine. Because we create the PR value in the sector argument, and it will live until the semicolon, and depending on that, then it's just perfectly fine, we don't need to decay. So really, max and min are perfectly fine it is, and it is the user of the composed projection, well not the user, the implementer of the composed projection, that should be responsible for preventing it. Because at this point, we've got the information whether we need it or not. So, solution 3. A composed projection never returns a reference to an intermediate PR value. So let's say clamp does the decay R value. So now clamp never returns an R value reference, and we avoid the problem. This is a bit too aggressive because like it's fine. Like if the R value just comes from the R value reference high or whatever, we don't need to decay it. So in fact, we only need to decay it if max returns a PR value. So we write the function decay if, which decays something if a boolean is true. And in this case, we want to decay it if max is not a reference. Because if max is a reference, we don't need to decay anything, it lives long enough. But if max is a PR value, we've got the dangling reference, then we need to decay. And this is like the minimal solution in order to decay. Right? This completely solves the problem without introducing any unnecessary moves, any unnecessary copies. Questions? Good. Because now the talk is going to go completely off the rails. Let's look at generic compositions. So this is a generic combinator. I've asked Connor about it. I don't know how to pronounce the name, but that's his name of the combinator. So it takes 3 functions, f, g, and h, and 2 arguments. And it modifies the first argument using g, and it modifies the second argument using h, and then passes both of them to f. And all f, g, and h are potentially projections. And so together we have a composed projection that projects one argument using one function, one argument using the other, and then combines them both using a binary function. And so here we run into the problem that like if G returns a PR value, F might potentially return an R value reference to the PR value, so we need to decay it. So we need to decay if G or H returns an PR value, right? Because then we potentially return an R value reference. But what if, let's say H is the identity function, and F is a function that always returns the second argument, and G returns a PR value. Then we don't need to decay, because we create a PR value, but we just throw it away, and we only return an R value reference to the R value reference that we passed in via U, passed in through the identity function, which is F. Right, so then we don't need to decay it. We only need to decay if F returns an R value to a PR value returned from G or H. Because if the PR value is created by G and we never return G, then we don't need to decay anything. The problem with that is we don't know that. Right? Just by looking at F, we don't know whether it returns an R value to a PR value reference from one of the arguments. Now this is a problem. But luckily this can be solved using my favorite mantra. C++ isn't a particularly great language, but all problems in C++ can be fixed with more C++. So the idea here is, let's enable this tracking of the referenceness using a special marker reference. So we introduce a type that indicates a reference to a temporary. The idea is then, whenever we create a PR value, we instead of creating a regular reference, we create this marker reference, pass that to F, and if F returns this marker reference, then we know it's the reference that came from the temporary, so we need to decay it. But if F just returns a regular reference, R value reference, then we know that we don't need to decay it. So this is that type. It's simply a wrapper of an R value reference, so it behaves exactly the same as an R value reference. It's explicitly constructible from an L value reference and implicitly constructible from another R value reference. And then if we use it as an L value, it stays an L value reference, right? Because R value references themselves aren't R values, they're L values, because they have a name and so on. And if we use it as an R value reference, then we only get an R value reference. Right? So this is this wrapper type. It's simply a marker type of an R value reference to indicate that points to a temporary. So now we've got three kinds of references: L value references, R value references, and TC temporary. We then want to create it. And to create it, we need a macro, because within a function we cannot distinguish between phi R values and R value references. So we have this macro TCP R value as temporary. TCP R value as temporary checks whether something is needs to be wrapped, and it needs to be wrapped if it's a PR value. Unless it's like a temporary PR value, then we don't need to wrap it again. So like if it's a reference or temporary, we keep it as is. Otherwise, we wrap it in a TC temporary, and then we just static cast to the result. And this takes an arbitrary expressions and turns it into a TC temporary if necessary. So let's take a look. If we call TCP R value as temporary with just an object, then it gets an interf. Because crucially, we're using like deckel type of the double parents. Because deckel type of an identifier has special rules that we don't want, so we have to turn it into, it's just annoying. So deckel type of object with parents is an int reference. We don't wrap it, we just keep it as an int reference. If we move it, we have an int ref, we keep it as is, because it's not a temporary, right? It's an actual R value reference. It's an X value. If we pass in an actual PR value, we wrap it into a TC temporary. Similar, if you have a function that returns a PR value, this wraps in a TC temporary. So now we can get the correct reference type out of it. And again, this is necessary because within a function, we cannot distinguish between L values, X values, and PR values. So we need to introduce the new type in order to make this distinction. And this is really nice because of copy elision. So in most cases, the macro expands to this expression, like static cast deckel type of the expression of the expression. And then if expression is an L value and X value, this expression casts to an L value or R value reference. But in general, if the expression is a PR value, then it's copy elision and it's essentially a no-op. So this static cast, deckel type with double parents, is a no-op in all cases. If we use static cast with single parents, however, then there are special rules for identifiers kick in, and then it looks at the type of the identifier, and if it's an L value reference, it casts it to an L value reference, and if it's an R value reference, it casts it to an R value reference, and then we implement it stood forward. It's really funny how like just the addition of like parents completely changes what this function does. Like the above one is a no-op, and the other one is an implementation of stood forward. C++ is such a great language. Anyways, now we've got our TC temporary. The fundamental rule about TC temporary is a TC temporary must never be returned from a function. Because by design, it's a reference that points to a temporary, And so when we return it, we've got dangling stuff going on. So let's introduce this macro, tcReturn temporary. It returns an expression that is potentially a temporary, but if it is a temporary, we're gonna decay it. And this prevents the returning of any and all temporaries by leaving regular rvalue references unchanged. Because those are fine, those can be returned. So we write tcReturn temporary object, we just do a static cast to an int reference because it's an lvalue, so this is a no-up. If we call a move object, static cast to an int rvalue reference, also a no-up. If you have a prvalue, static cast to int, this is also no-up because of copylision. Only if you have a tc temporary, or most likely a temporary return from a function, then we do an actual decay. This will do an actual move, but this move is unavailable because for safety we need to decay it. And so because both return temporary and like prvalue as temporaries are macros that expands to a static cast, they have absolutely zero overhead. Because thanks to copylision, in most cases the static cast is a no-op. And only if we actually deal with temporaries do we need to actually do some work, which is really nice. Right? And because the macros, we don't have any intermediate function calls in debug mode or whatever, it just completely goes away. And so we can safely implement the combinator by, before calling f, wrapping the calls with prvalue as temporary to potentially create the temporary arguments, and then tcReturn temporary to decay them if necessary. And with that, we've implemented the introspection that we wanted. Because if, let's say, this is the signature of f, which is the one of our max or min functions, it returns the common reference. And because of the way everything interacts, the common reference of at least one temporary is a temporary itself. And so this will return a temporary, but at least one argument is temporary. In this case, we will need to decay, but it's fine because this is what we need to do. If f is a function that, let's say, always returns the first argument, then we can detect that in our combinator and know not to decay it. Because even if we pass a temporary for the second argument, a prvalue for the second argument, right, we don't need to decay it as long as the first one isn't. Right? So it completely avoids any unnecessary moves. This is why we did this. Right? This enables the introspection of the signature of the thing. And if we have something that always returns a prvalue, we will just forward that prvalue, and thanks to copylision, this doesn't add any overhead, because again, it's just a static cast, everything just disappears away. So we only have the minimal amount of overhead process necessary, like only if we actually need to decay, because we created a dangling reference to a temporary, which we can detect, do we actually need to decay, right? Just by using those macros, which is really convenient. Any questions? Okay. Now this is a generic function. And a generic function, it probably cannot call the functions directly anyway. Right? It needs to use invoke. So we can just go ahead and teach this handling to invoke. And then we don't need to worry about it. Of course, the consequence, because invoke needs to handle temporaries, invoke needs to be a macro, because otherwise we cannot handle temporaries. And let's say like our invoke implementation just wraps all the argument into prvalue as temporary. And then we don't need to do it at the call side, it just invoke does it for us. The actual implementation uses Boost preprocessor, of course, which is a lot of fun. But essentially it works. And then we can just, because we need to invoke anyway, we can just write it like so. So invoke G with T, invoke H with U, and invoke F with the result of the two invokes. And then we just want to say that return a temporary to decay it if necessary. And we don't have to worry about the creation of the temporaries, because this is just handled for us. Right? This is a nice simplification. So this is on the generic side of the composition. Right? As a necessary consequence, all projections now need to be aware that they can be called with tc temporary. Right? We've introduced this new reference type, they all need to handle it. This isn't a problem for max. Right? Max as written just works, because like it's implicitly convertible to a reference, so the comparison just triggers the thing, and then common reference just handles it automatically. So max as written just works. The problem with is a function like getFoo, which calls object getFoo. Because we introduced a new reference type, we don't get the behavior like references, we can call .foo, but like on our reference, it's not a reference, we can't do it. So we need to be aware of that, right? We need to change it. Right? In particular, in order to call foo, we need to like unwrap the temporary. We can do that with yet another macro. So unwrap temporary takes an expression, and if it is a temporary, we will return the underlying reference. So we will then static cast it to the underlying reference of the temporary, and otherwise we just static cast it to Jekyll type of the expression itself, which is another no-op. If it's not a temporary, everything just falls away, compilation, cast to reference, and so on. And now getFoo needs to be like unwrap temporary of the object, and then we can call that foo in order to do it. Of course, if we unwrap it, we lose the information that it's a temporary, right? So if getFoo is called on a temporary, we want to preserve that information and want to indicate that the result is also a potential temporary. But we lost it. So we need to rewrap. Rewrap is a bit more complicated because whether or not we want to rewrap depends on whether the arguments were temporary. So rewrap takes a bunch of arguments and an expression. And if that expression is an r-value reference and any of the arguments are p or r-value, or rather a temporary, because we cannot detect p r-values, then we need to also wrap that in a temporary. Because we assume that the lifetime of the expression is sort of tied to the lifetime of the arguments we specified, which is a heuristic, but it works. And so we then need to rewrap it back again into temporary. Yeah. This is a heuristic. Like we can't look into the expression directly because it's a projection that isn't aware of the temporary handling, right? Member access doesn't know what TC temporary is, so we have to implement the logic ourselves. But with that, we need to write projections like so. So getFoo first unwraps to do the member access and then rewraps. And we say that if the original thing was a temporary, the result also needs to be a temporary in order to preserve the lifetime information in order to make it all work. And this approach works. When we write compose projections, we need to use TC invoke and TC return temporary to prevent returning of dangling reference. TC invoke wraps it all in TC temporary objects, so we can pass that to the function and then look at the return type to figure out whether it is one of those temporaries, and then return the case stamp, so we never return a dangling reference. And when we implement a projection, we need to be ensured that the tracking is accurate, so we need to unwrap and rewrap as necessary to prevent any unnecessary decay. The consequence, of course, is that all templated projections need to be aware of TC temporary, which is a bit annoying. But, you know, it works. And we could implement clamp that way by using return temporary together with PR-value as reference to do the appropriate logic. It just works in a generic way. We don't need to know anything about the functions and how they behave, whether we return both arguments or none. Questions? Okay. Now, the thing about template projections is a bit annoying. That suddenly we have to do unwrap and rewrap all the time. But it's not really all templated projections. TC temporary is only relevant for projections that could ever return an r-value reference. If a projection never returns an r-value reference, we don't need to decay anything, and then it doesn't need to deal with temporaries at all, because the lifetime always works. Right? It's only the projections that potentially return an r-value reference. And those are really rare, because in most cases, you just return a PR value. Let's say you want to have a function that just adds something to 2, like increments the thing and returns like thing plus 1, right? That's a PR value. We don't need to be aware of TC temporary. And so the vast majority of projections can completely ignore TC temporary. The problem is we're still giving them TC temporaries, even though they don't need them at all, right? We can just give them regular references and they're still fine because the lifetime just works out. So we can actually implement it by doing a thing in invoke. So we first invoke the function without any temporary arguments. And if the result is an r-value reference, then we're in dangerous territory, because then the function potentially returns an r-value reference that is derived from one of the arguments. And then we can't actually do the unwrap, and we actually have to give it the temporaries, because it needs to be aware, it needs to handle temporaries. But if we call the function and none of the arguments are temporaries, if you call the function with no temporary arguments, and the result is not an r-value reference, we're good, right? We would never need to decay anything anyway, so we can might as well just call the function without temporary arguments, so the function doesn't need to be aware. So only the functions that potentially return r-value references are ever instantiated with temporary arguments, and everything else just isn't aware of the thing at all. And this optimization actually made it feasible to just apply this thing in our code base. Because the vast majority of projections that are written in all of our application code fall in the second case. They don't return r-value references, so they're absolutely don't need to know about the existence of TC temporary, and you can just write regular code that just takes regular references and write regular C++ code. Only the projections that are generic enough to properly annotate lifetime need to be aware of TC temporary, and all of those are highly generic functions in our core libraries anyway. Things like max, min, trim left, trim right, and so on. So this worked out really nicely. One problem remains though, and that is when we now compose our projections further. So this is our composed projection, and let's say we compose it with something else, and suddenly it gets called with a TC temporary. And then T or U themselves are TC temporary objects. And then our logic breaks, because let's say G or H don't return PR values, they just pass through. But then we would decay a temporary that's passed in from the outside, which is completely unnecessary because it's not the dangerous case. So to prevent that, we need to change the definition of temporary by introducing a lifetime. So a temporary of some T has some lifetime. And if it has a lifetime of 0, that is the temporary that we need to decay in TC return temporary. That is a temporary that we created. But if it's the lifetime greater than 0, it's a temporary that came from some higher scope. And then we can just treat it as a regular R-value reference, just pass it on. And then the caller needs to decay it. And then we also change common reference and reverb temporary to use the minimum lifetime of all temporaries to do the appropriate logic and so on. And crucially, every time we call a function, we need to use increment lifetime, and every time we exit the function, we call decrement lifetime. So we create our temporaries as temporary 0, pass them on to another function. This turns it into temporary 1, which means that the function just passes them on, returns it, decrements the lifetime, and we end up with our temporary 0 again. And that way, they passed in on completely transparently. And all of this increment and decrement can again happen in vogue, right? Because this is the point where we actually call the function. So when our arguments are already temporaries, we increment the lifetime to turn them as temporary 1s or higher to prevent the function from like interacting with them in any way. They shouldn't decay it. Then we return it back as 0. And if we get a 0 on the call side, we know this is one of our temporaries. We're responsible for it. We need to decay it. And otherwise, and again, like if we don't care about temporaries, we just unwrap. And this handles the nesting. The talk title was Overengineering, you know, in case you. Okay. Any questions? Yes.
The if context where why do you need to call TC unwrap temporary on the arguments?
Right.
Not when you return the actual.
Okay. The if const expr, I want to, if you've written a generic function that never returns an R-value reference, I don't want you, as the author of the generic functions, to deal with the existence of TC temporary at all. Because then you would need to like unwrap and rewrap. Right? And I can avoid that work for you because you're safe, right? Anyway, I don't need to translate that information. So I want to prevent instantiation of your function with temporaries. So I check, if I call this function without any temporaries, do you return an R-value reference? And if you don't, you're completely fine. You will never get instantiated with temporaries. But if you do, I need to know whether this R-value reference comes from somewhere else or from one of my temporary arguments. And so when this returns an R-value reference, I need to call it without unwrapped temporaries in order to preserve that information. Any other questions? Okay. Now, I've glossed over some complexities. Our temporary also supports const qualified R-value references. Not just non-const, and then it has some additional information. And we implement reference collapsing rules. So regular references are quite nice because if you have an R-value reference, it is always treated as an L-value. And so likewise, when you have an L-value of a TC temporary, we really want that to be treated just as a regular L-value reference. Because in whatever context you are right now, it is an L-value, you don't need to deal with it as a temporary. So it automatically, by all the relevant traits, gets turned into an L-value reference. And similarly, we don't want to distinguish between an R-value reference to a TC temporary and like a PR-value TC temporary, because a TC temporary by itself is already a reference, like we don't want to add references to it. So we keep it as is. This is similar to the rule about like regular reference collapsing. Like if you have an R-value reference and you add an ampersand to it, you get an L-value reference. And if you add like another R-value reference, you don't have an R-value reference to an R-value reference, you just have an R-value reference. Unfortunately, we had to do that with metaprogramming because the language, but hey, it's C++, at least it's possible. And we actually used that in production. We have implemented this TC temporary mechanism in order to solve the problem of unnecessary decays or eager decays or dangling references. It's really only necessary for function objects in linear code, like max or min and so on. The composed projections all handle temporaries appropriately, and because the vast majority aren't that generic, they don't care about it at all. Only the generic library projections need to handle it appropriately, and there isn't a single projection in user code that needs to handle temporary. So all application code outside the library doesn't need to know that TC temporary even exists, it just magically works. And this is a big thanks to one of the favorite macros in our code base, a function that creates a lambda. So this is TC member, we can use it like so, transform a range by calling .foo, and this generates a macro that just calls .foo on the argument. And this needs to do the logic of like unwrapping and rewrapping temporaries. It's used in all over the places, and it does the appropriate lifetime. And because a bunch of people just write projections like that, they don't need to worry about TC temporary, I did that for them, right? It's really convenient. Similarly, we have TC memfun, which actually calls it with some arguments, and I also implemented the appropriate temporary logic there. And a bunch of other generic function objects that we provide all handle it automatically in order to just make it work, right? So when I deployed the TC temporary change, nothing in application code needed to change, even though we suddenly had temporaries, we introduced a whole new kind of references without anybody being aware, until you want to actually do the optimization and return functions that preserve R-value references, then you need to be aware. But it just happens that all of those are in our standard library anyway. Now at this point, like, there's a relevant question, like, what are we even doing here? Right? I mean, we solved the problem because it's C++, so of course we can solve the problem, but like, this is a mess. Like let's backtrack. What we wanted to do is we wanted to avoid unnecessary copies, and we wanted to avoid unnecessary moves. And when we then compose that, we don't want to return a reference to intermediate temporaries. And then we ran into this problem that how to track whether the resulting reference is tied to an argument. And because we have no way of tracking it, we had to implement this whole new type in order to track it. And like, of course, there's the obvious thing, like Rust solves it, right? In Rust, you've got lifetime annotations. So let's say this is some C++ syntax with lifetime annotations. So let's say max has two references with a lifetime, and then we say that the result is a common reference with the same lifetime. And let's say, like, Rust doesn't really run into the problem of like having a common reference, like sometimes return a reference and sometimes return a type. This is not expressible with them. So let's just say that here, if common reference is actually a non-reference, then the lifetime annotation does nothing. So if it returns a PR value, it doesn't have any lifetime annotation. But if it has one, then it comes from the arguments. Right? And then the compiler can just look at the signature and know whether the resulting reference comes from one of the arguments without having to introduce this whole TC temporary thing. Right? This was the entire reason. And then we can just say the obvious rule that, hey, compiler, it's silly to return a reference to a dangling temporary. Don't do that. Right? And the compiler can actually figure it out because it can look at the signature of f, sees that it might be instantiated with a lifetime that came from one of the arguments or whatever. And if so, it can keep it. But if it returns a reference that came from one of the PR values created inside, then it decays it. Right? Just help me out. It can't do that in C++ because the compiler can't look into f to figure out whether the reference that is being returned comes from one of the arguments or not. Right? This is why we implemented the TC temporary tracking. But if f has like the appropriate lifetime annotations, the compiler can look into it and figure out what went wrong there. And this would just solve the problem, right? We just add lifetime annotation. This is what Rust does. But this is still unnecessary complexity. Like we just wanted to write max. Why do I have to deal with all this? Right? Because of course, like, don't return a reference to a dangling temporary. Right? That would be silly. I never want to do it. Right? And now the question is, why does Rust require lifetime annotations in the signature? Why do you have to deal with it? Well, because in general, it's there to prevent you accidentally changing the signature during internal refactorings. Right? So let's say you have a function version 1, which never returns a reference to the second argument. But then you did some implementation changes and accidentally you changed it. So suddenly it can also return a reference to the second argument, not just the first. And to prevent that, you have to like promise in your signature what your lifetime is. because then internal refactorings like that become a breaking change, because they are a breaking change. Right? You can't just suddenly return different references to different arguments. That wasn't the case before. But like if you write a projection like max, such a change is like, would be a breaking change anyway, because we're changing what the function does, right? If you have a function, a projection that like never returns a reference to the second argument, and then we change it so it suddenly returns, like it's an entirely different function. Like if let's say it's projection second that always returns the second argument, and then we did some changes, and now it sometimes returns a reference to the first argument. We broke the function anyway, right? So we don't need to promise it in the signature, because the lifetime behavior follows from what the function does. Like max always can return a reference to both arguments. Second can never return a reference to the first argument. This is just what the function does. So here we don't really need lifetime annotations. And then the second thing is, like, why do we need to like do something to call by reference? Like call by reference is just, we want to avoid a copy, so we call by reference. Why doesn't the compiler do that for us? Well, it has complexities for lifetime tracking. Like it's an observable difference, we need to be aware of that. But for projection, there's an obvious choice. Like we just want to get the values out. So just parse them, and please parse them in the most optimal way. By reference, by value, whatever, I don't care. Like I don't want to care, I just want to write my function. So the better approach is to just write the projection. So with this hypothetical syntax, we would just say, hey, max is a projection. It takes two values, returns the max one, and returns the comment type. And then the compiler just figures out, oh, I'm passing actually two string lvalue references, so I don't need to create copies, I can just return it as an lvalue reference. Right? We sort of promise that thing with the projection. Like, why do I have to deal about that? Right? There's an obvious choice, and all I did, all this complexity was just to enable the obvious choice that I wanted to do here. And similarly with a compose projection, because with a projection, let's say the compiler is required to like infer the lifetime tracking of the signature by looking into it, so you have to define it in a header, but that is fine or whatever, and then it can just figure it out. Right? And then we can just write the projections and don't have to worry about it. Like, this is the code I want to write. I don't want to deal with TC temporary. I don't want to do all this macro metaprogramming in order to just get basic lifetime tracking in order to write unnecessary copies and unnecessary moves. And this is a much cleaner choice. And this is why I say the worst feature C++ has ever added are first-class references. Like the existence of references to C++ is such a pain. Like it's a complexity in function arguments. So every time you have a function, you have to think about, do I pass by reference, do I pass by value, do I pass by rvalue reference, do I pass by forwarding reference? Yeah, the entire thing, reference, lvalue reference, forwarding reference. Temporary lifetime extension is a whole mess in on itself that could be entirely avoided. We've got dangling references. If you don't have references, you don't have dangling references. So that's solved. And there's so much complexity in every language feature. Like every time you change the language, you have to think about references. Like the original concepts had you specify signatures. So you say, I want to require that the function foo takes an int and a float. But this got complexity because the function doesn't need to take an int and a float, right? It could take a constant lvalue reference to an int, and then you could also call it. And this approach just doesn't work. And just so annoying. Like I wish references were added to solve the problem of operator overloading. Like you want to implement the dereference operator, so you have to return an lvalue. Well, a regular function result isn't an lvalue, so let's implement a thing that is. And then just follow it from there. And like if you solve this problem in a different way, it would be so much nicer. And in this particular case, I just want parameter passing modes, right? I want to say this is an input argument, this is an output argument, this is an argument that I modify, right? And then the compiler just figures out, right? I don't need first-class references for that. Just have the compiler figure it out. And this is why I'm like really excited about Hilo. Because Hilo actually takes this word. Like references aren't a thing, you just do value semantics. And then whether you pass by value or you pass by reference, this is an optimization. Semantically, all you do is copies. But in the implementation, you do moves, you do pass by reference, and so on. And they actually have like projections, and they call them subscript. They have them as a first-class features with the exact semantics as described. So if you define max in Hilo as a subscript, the compiler will just do the optimal thing to figure out how to do all the lifetime tracking. And this is a so much cleaner design. Like I spent so long on this thing just to get like the optimal performance out of there. And like if the compiler just does it for me, this would be so much nicer. Like why do I have to deal with all this complexity? Anyways, that concludes my rant about language design. We were implementing max at some point. So let's get back to that. This is the implementation of max we ended up with. It returns the common reference, conditional, so on, just to make it all work. The actual max, you can pass in like a comparison function. So you can optimize it. So let's do that too. So let's call this best. So best does not return the maximum, it returns the best value. And the best value is determined by checking whether one value is better or another. And like better is a custom strict Greek ordering, and we then just return the better of the two values. And then max is just best, where the greater one is the better one, and then we also have min, where it's the less one, right? This is a very straightforward change. But now that we have a predicate, we can do something fun. Because we can implement a compile time predicate. So let's say we call better. If better can do the check entirely at compile time, then we can say, okay, so if this is true type, then we always return B. If it is false type, because A is all guaranteed at compile time to be worse than A, then we return A. And otherwise, we do the dynamic way. This has the interesting consequence that we no longer require like a comma type between the two, because if you can do the comparison entirely at compile time, the function returns different types entirely. And it doesn't matter. We will see a use case soon. And this is another thing that bugs me about like, because the byte doesn't return a way to do that, right? In principle, we could do all this logic in the ternary operator. So in our custom macro, we could say that, hey, we do the comparison at compile time to do the thing, and otherwise we do it at runtime. We can't, like, we could implement it like that, but this creates an intermediate stack frame because of the immediate invoked lambda, and I don't like it. So I'm really looking forward to having like context by ternary operator or do expressions to allow us to just write that in line, right? I just want to say that if the ternary operator, like if the condition is like known at compile time, it should just select the thing at compile time and don't require a comment type. This would be useful. It would be useful, for example, we want to say that the best type is the one that's bigger, right? So this is the type that returns the biggest size, and the predicate can be entirely evaluated at compile time, return true type or false type, depending on the condition, and then we get the value of the type of the bigger size. Double and const sharp pointer don't have a comment type, but we don't need it because we can do the check entirely at compile time. And this is really useful because you sometimes want this. So like also we use this technique a lot in our code base. So for example, when we filter a range, we can filter it by a compile time predicate. And because our ranges, like a tuple is a range, so we can have a range of different types, and then we can filter them based on like the type properties, and then we can manipulate type list entirely using ranges by using tricks like this, where like the predicate is a compile time constant, and then we switch to an if context bar instead of another one. It's a neat trick. And then of course, the final change that we want to do is let's make it very realistic, right? So why not 2 arguments, why not arbitrary many? And so we sort of do like a fold. Right? So better, maybe we do the compile time check, and then we pick the better one and check it against everything else, and then we do it at random. And that's really useful because now we can actually do the maximum of arbitrary many arguments. Anyways, I think I've done enough max implementation at this point. So let's backtrack again. Is this all really necessary? Like all this lifetime tracking, do we really need it? Well, if you want to avoid unnecessary moves, then yes, right? You need something like TC temporary because returning R values is really dangerous when writing generic compositions, right? You need some form of lifetime tracking. But if you say, okay, I'm fine with unnecessary moves, all my types are cheaply movable, then you can decay. And if you always decay R values, then it's fine. So, but I mean, really, we just need different language design, right? This is just complexity that is so unnecessary because the compiler can figure it out, right? Why do I have to care about it? So anyways, we're using this in production. So like all of the temporary stuff is available on our GitHub library. So we actually want to see how it's done, or God forbid, use it yourself. You can find it over there. We're also hiring. I still got some socks. I got some flyers. I know at least somebody was interested in the flyer, so find me if you want that. We have a developer blog. And you will eventually find the slides over there. The URL isn't live yet. I need to write the website. Thank you.